Let's now continue with our PID example. So I've copied the problem statement and our system here for reference in this video, so you can pause the video to remind yourself what we're doing. And I've got some key results from our previous video as well. So we said that 20% overshoot corresponded to a zeta of 0.456, and we also previously found our peak time to be 0.297 seconds for our uncompensated system. So we're going to pick up with step 2 of the design, and this is going to be design our PD controller. And so of course here what we're trying to adjust is our transient response. And so as given in the problem statement, we want to reduce our peak time to 2/3 of the uncompensated peak time. So all we need to do is multiply this peak time by 2/3, and we find that our new desired peak time is going to be approximately equal to 0.198 seconds. And so we know that that 0.198 seconds for our peak time is equal to pi over our imaginary part, but our imaginary part of our pole, we also know that we can write that as the variable omega d. So we've seen that previously when we were talking about our time response. And so of course we can just then solve for our omega d, which again is our imaginary part of the pole, and we get that that is approximately 15.858. And units on that are going to be radians per second, but we're just looking at it in terms of a pole location. So now, of course, we want to maintain this same 20% overshoot as we compensate the system. So what that means is we're going to have this same damping ratio. And in terms of our S-plane, that means we're going to be on the same radial line. So we're going to have some triangle here, some right triangle. And so the angle theta is going to be the same angle theta that we had for our original system. And so now our imaginary part is going to be omega d, and let's call this our sigma sub n. And so that angle theta is related to our damping ratio. So it's going to be the inverse cosine of our damping ratio, which was the 0.456 that we found in the previous video. And if we evaluate that, we see that angle theta is approximately 62.871 degrees. Okay, so now we can use trig to figure out our sigma sub n value. So we can say that our tan of theta, so tan theta is opposite over adjacent, so that's going to be equal to omega d divided by sigma n. And from that, we can see that our sigma n is going to be equal to omega d divided by tan of theta. And we plug that in, we get it's approximately 15.858 divided by tangent of the 62.871 degrees, and that gives us a sigma n of approximately 8.125. Now, of course, remember that's going to be negative when we talk about in terms of a pole location. So what that means is our desired new dominant poles are going to be at, so we have our real part is going to be negative 8.125, and now we have plus or minus j times that imaginary part, which was 15.858. Okay, so now we know where we want to be in terms of our pole location, but our root locus doesn't go through that point. So in order to make it to go through that point, we know from our PD design we need to add a compensator 0. So we need a compensator 0, and so we know that's going to have the form of s plus z sub c, but the question is, where do we put that z sub c? And we want, of course, that point to be on our root locus. So what we want to do then is we can consider the angular contributions from all of our existing poles and zeros, and then we can, from that information, determine where our 0 needs to be, such that the overall angular contribution is going to be an odd multiple of 180. Okay, so let's say this is our desired pole location. So remember, this is negative 8.125 plus or minus j 15.858. And I'm going to put down here, so this is essentially my real axis sigma, and I'm going to put all of our pole and 0 information from our original system. So we have our pole at negative 8, or sorry, a 0 at negative 8, and poles at negative 3, negative 6, and negative 10. So of course we can see that so let's come down here and let's put our negative 10 is going to be over here. Our 0 at negative 8 is just going to be barely to the right of that desired pole location. And then we have two other ones at -6 and -3. So let's just go ahead and label -10, -8, -6, and -3. And of course, what we're doing to find that angular contribution is we are drawing a line from the poles to each of those points, and we're saying the angle from our positive real axis is going to be the angular contribution. So this would be our angle theta sub P1 from our pole 1. So we do a similar thing for each of our other poles and zeros of our open loop system. So this is going to be theta P2, so the angular contributions from our second pole. And similar thing here for our zero, so this is going to be theta Z1. And finally, from this guy right here, we're going to have a theta P3. So now we need to use trig to figure out these angles. And so like we saw previously, we're going to sort of create these right triangles. So for instance, if we're interested in P1, we can create some right triangle by coming straight down here, following along this line and doing this. And we'll look at that triangle. The other triangles we're going to look at, of course, similar thing for our theta P2, so that's almost the exact same approach. And same thing for this theta Z1, slightly different for our theta P3 because now our angle is inside of the triangle, but same basic idea. Okay, so let's look at the triangle explicitly for that theta P1, and then the others I'm just going to write the equation. So for our theta P1, we have our 15.85, a little too slow drawing that out there. Okay, so we have something that looks like this. So this is going to be our 15.858 for this part of our triangle. Down here, we're going to have our 8.125 minus 3, because again, this is the distance between sort of that real part of our pole and -3. And of course, we have our angle of interest is outside the triangle, so it's going to be this angle here, theta P1. So, as we saw previously, we can say our theta P1 is equal to 180 degrees minus the inverse tangent of the opposite over adjacent, where we have 15.858 divided by our 8.125 minus 3. And the reason we had this 180 degrees minus is just, again, because that theta P1 is outside, so the inverse tan gives us this angle inside, but we want to subtract that from 180 to get our theta P1. So if we plug all of that into the calculator, we end up with a theta P1 of 107.91 degrees. Okay, so same basic process making right triangles for those other angles. Again, I'm not going to draw the triangles out explicitly. You can do that for practice, and if you run into issues, let me know. But for our theta P2, we have 180 degrees minus the inverse tangent of 15.858. So we're always going to have that as our height of this triangle. And now we have 8.125 minus 6. So the only thing we changed is we're subtracting 6. So basically, we just have a different length of this bottom segment. So we evaluate that, and we get that that is approximately 97.63 degrees. All right, so on to theta Z1, so for our 0. So we have 180 degrees minus inverse tangent, and again, same numerator, 15.858 divided by 8.125. And now we're subtracting 8, because that's where our 0 location is up here. Plug that in, and we get that that is approximately 90.45 degrees. And so it's always a good idea to sort of do a sanity check to make sure that these numbers you're getting look reasonable based on the location. So we would expect that to be a little above 90, which we see there. And of course, we would expect this to be a little bit more above 90, and we would expect this to be well above 90. And so we're seeing that is true for all of these. So finally, we look at our theta P3. And so this one is going to be, again, a little bit different because the angle is inside of that triangle. So we get inverse tangent of 15.858 divided by 8.125 minus, sorry, I've got that backwards. So now we're switching it up a little bit. So now it's 10 minus 8.125. And so we plug that in to evaluate, and we get that that is approximately 83.26 degrees. Okay, so now what we do is we're going to sum all of these angular contributions. And so remember, what we want is we want the sum of our 0 angles minus the sum of our pole angles to be equal to some odd multiple of 180. But of course, right now we don't have that, so let's just go ahead and see what we have. So we put, this is our only 0 angle, so we're going to have 90.45. So let me go ahead and write this out for clarity. So we have 90.45 degrees, which is going to be subtracting 107.91 plus our 97.63 degrees plus our 83.26 degrees. And so if we plug all of that in, we see it's about negative 198.35 degrees. So obviously that's not an odd multiple of 180. So that means that our point is not on the root locus. So let's say we want an odd multiple of 180 for our point to be on the root locus. And so what we're going to do is we're going to choose the closest odd multiple of 180. In this case, it's negative 180. So we can say that the angular contribution from our 0 for our compensator has to be the difference between, well, let me write that a little bit differently. So let's say the sum, so we're adding our theta ZC to the sum of 0 angles. So in other words, we're just going to add this theta CZ to our overall contribution here. So we have theta ZC minus our 198, or rather plus the negative 198.35 degrees, and we're saying that needs to be an odd multiple of 180. The closest odd multiple of 180 is negative 180, and so that gives us our theta sub ZC of approximately 18.35 degrees. Okay, so now we know the angle that we need, but where does that mean that our 0 is at? So of course, looking at this diagram here, if we have an angle, of 18.35, we know that's going to be fairly far to the left, but let's again use our geometry to figure out exactly where that position is going to be. All right, so let's draw a triangle like this, and again, this is going to be a right triangle. We have 15.858 here, and so this is our angle theta sub ZC, and now our base of the triangle is going to be our 0 location minus 8.125. So what we can say is that our ZC is going to be equal to our 15.858 divided by the tangent of that angle theta sub ZC, which we found above to be 18.35 degrees, plus our 8.125. So if we plug this in, we get that this gives us approximately 55.94. Now, of course, the actual 0 location is going to be negative 55.94. So we could say our GDP, so our compensation transfer function, remember it's going to have the basic form as we talked about here, so just S plus that 0 location. So we could say that our G sub PD, so our PD compensation system of S, is equal to S plus 55.94. Okay, so there's the design of our PD controller. Before we move on to the next part in the next video, let's characterize our system again. So, of course, as we've seen before, when we do this, we're going to be adjusting our root locus. So we've added an additional 0, so of course the shape of our root locus is going to change. And so I'm going to attempt to plot this, but the scale is a little large on one of the points, of course, having that 0 at negative 54. And we also have a break-in point much further, but let me just roughly attempt to plot this. So let's do, this is going to be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so let's say negative 20, negative 40, negative 60, negative 80, and negative 100. And the reason I've gone out so far is because we're going to have a break-in point a little further towards that side So again, I wouldn't have expected you to know that. Of course, what we want to do is go to MATLAB and plot this. Okay, so let's add some of our open loop information. So now remember, we've updated our G. So we've multiplied our original G equation by this G sub PID, our compensation. So we now have this extra zero at 55.94. So let's say this is going to be roughly, so there's 50, so about somewhere right here. And so that's a zero, not a pole. So we have a zero at this location. We know from our original system, we also have a zero at 8. So let's say, that's right about there. We have a pole at 10. We have a pole at -6 and a pole at -3. So now we get something that looks like this. So we can plot our root locus. So let's come in here and plot our root locus. So based on our rules, we know it's going to be on the real axis in this region, and everywhere to the left of this zero here. Okay, so we get something that looks like that. Okay, so let's see. So now what we can do is, again, we're still going to have in this region here, it's sort of self-contained, that pole is just going towards that zero. And what we're going to have is between our poles at -3 and -6, we're going to have some breakaway point. And so it turns out that the break-in point is coming back in at about -106. So that's why I drew this sort of so far this way. One of the points is going to continue going this way, and one is going to be coming back towards our zero. So again, not a super accurate drawing, but maybe we get something that looks like that. And of course, that should be symmetrical about our real axis, and so I've already kind of messed that up. Let's do a little bit better maybe. So we get something that looks like that for our root locus. Now, of course, what we're interested in is the intersection of that with our damping ratio line. So again, let me try to draw this roughly accurately. So our damping ratio line actually intersects this root locus at 2 points. And so it turns out that it's the first point that we're interested in. So this is 0.456. So we're interested in this point right here. And so that's just because when we plot that, we can see that that is closer to the dominant pole that we calculated way back up here. Okay, so this is just sort of to give you a rough idea of what the root locus looks like. Of course, what we would want to do is we could go to MATLAB and we could use our rlocus function. We use our sgrid function with z and 0 to get that radial line. And then we can use the rlocfind function. And of course, for that, we have a gain and poles as our output. And that, of course, needs to be of our updated transfer function, open loop transfer function, G. Okay, so if we do that and we investigate this pole location here of interest, what we find is, again, remember that there is potentially some user error in selecting these points, but I found that we have a dominant set of poles at -8.14 plus or minus J15.90. So these are the actual dominant poles as measured from MATLAB. So dominant poles after inserting that compensator 0. So it turns out we get that at a gain, K, that's equal to 5.356. So notice that value is a lot smaller than the gain of 121 that we saw last time. Our third pole, so we have 3 poles in this system, so our third pole in this case is at a location of -8.079. So we would have one pole where I've highlighted there, a second pole down here, and then our third pole we're saying is, right above that 0. So again, it is approximately canceling out with that 0. So approximately cancels with our 0 at -8. And so what that means is our second order approximation is okay. We do have that 0 further out at -55, so we want to be aware that our second order approximation isn't going to be as accurate, and so we'll talk about that here in a minute, how we can sort of verify the accuracy of this. Okay, so I'm not going to go through all the details of calculating these values, but using our second order approximation, we can calculate settling time, peak time, steady state error, all of that stuff. So if we go through that, we would find that our settling time, which is again just 4 over the real part, is approximately 0.4492. It looks like I have written, I might had that number a little bit wrong, but I believe that's a 9, 4.92. Our peak time is going to be approximately 0.198. So remember, that's what we sort of set out to design. So of course, if we scroll back up to our desired peak time, so quite a ways up here. So this was our uncompensated peak time, and we said this was our goal peak time. So we did achieve that 0.198 seconds, so that is good. So we've got our peak time of 0.190 seconds from pi over the imaginary part. And we can also talk about, again, our steady state error. So our k sub p is still going to be that k, so we're still going to have k times 8, but now we have a new zero, so we have our 55.94, because remember this is our compensated g, and in the denominator we still have 3 times 6 times 10. But remember, now our k value has changed, so now our k value is this 5.356, and so if we plug that in, we get that our kp is approximately 13.32. So our steady state error equation is still 1 over 1 plus kp, but of course now our kp has changed slightly. So we get that our steady state error now is approximately 0.070. So let's compare that to the uncompensated system. So compare to our steady state error for the uncompensated system, which was 0.156. So what we see is we've actually improved our steady state error a little bit. So improvement in our steady state error. Now, of course, the problem specified that we want a 0 steady state error, so we're still going to have to come back and improve that further. But this sort of is an important point to note, that as we're changing transient response or steady state error, we're inevitably going to be making slight adjustments to the other parameter. Okay, so that covers our step 2. So let's briefly talk about steps 3 and 4 to conclude this second video. So steps 3 and 4 in our general PID control process, or our design process, is going to be to simulate and redesign if needed. Simulate and redesign if needed. And so I'm going to come back and we're going to look at a plot of our step responses a little later on, but the basic idea is we would want to plot our step responses. So we have our g functions in MATLAB, right? So we had, for instance, our g is equal to transfer function of whatever the numerator is, whatever our denominator is. And remember, as we added that PD compensation, we had to adjust this numerator because we added a 0. So if we want to plot the step response, we need the closed loop transfer function. So for instance, we could say our T1 is equal to feedback, because we had a feedback configuration, unity feedback. And in that block, we're going to have to introduce, of course, our gain. So this gain here for our T1 would be that approximately 121 times our G uncompensated. So let me say maybe UNC. And our feedback path was unity, so we just have 1. Our T2, we then use our updated G and our updated gain. So we still need to include that gain. And so in this case, our gain was the 5.4, let's say, about 5.4. Of course, you can plug in the more approximate value in MATLAB. And this was our G compensated. And let's be more specific, it was just our PD compensation. We still had a unity feedback path, so we get something that looks like this. So once we have those two closed loop transfer functions, in MATLAB, we can just say step of T1 and T2, and that's going to give us the step response of our uncompensated and compensated system respectively. So as I said, what we're going to do is we're going to wait until the very end, and we're going to look at the step responses of all 3 of our systems, uncompensated, PD compensated, and PID compensated. However, I'll just go ahead and say, of course, as you would expect, looking at these 2 step responses here, we do see a reduction in our peak time. We also see the reduction in our steady state error, but we'll take a closer look at that a little bit later on.